Now, today we have one major mission, which is to finish as much as we can products of inertia with one or two examples. And after that, I'm going to show you how we use moments of inertia and products of inertia on any arbitrary objects. If you don't know what we call the principal axis of inertia. And that's, if I have time, I will define that in example 34. So that's our plan today. Now, starting with products of inertia, I talk about the concept that for any arbitrary objects, suppose I have to find some irregular. All right. How about this one? Like this paper, this irregular shape kitchen napkin, I wrap it like this. Now, if I ask you what is the principal axis of this eraser, you probably can guess, right? You're gonna guess maybe the longitudinal axis and also the perpendicular one, another one like this, and you're right. Why? Because the shape is regular. For regular shape objects, it's easy to determine and to estimate principal axis of inertia. But for any arbitrary shapes, like this, doesn't have any obvious axis of symmetry, how can we know what will be the axis of principal axis of inertia? To do that, we will have to use example 34. I will show you the technique, how to do it. Okay, then so let's consider one example. I'm going to start this example by calculating principle of, mass moment of inertia. And then we're going to calculate products of inertia. So you're going to see the difference between these two. And this is what this example would look like. Consider a three-dimensional, you may call it a wedge. It's a triangular shape. Looks like this. Dimension-wise, on the x and y axis, it has dimension A. But on the z-axis, the height of this wedge is h. And notice that they are not all the same. And of course, you can consider this is a volume, and we want to calculate different things. And just to be complete, we want to find everything about this three-dimensional wedge, this wedge. We want to know everything. I, x, x, I, y, y, I, z, z, I, x, y, I, y, z, and I, z, x. That's all we can know, right? Now, if you haven't noticed, or what I said last time, and that was last Friday, IXX, IYY, IZZ are basically what we calculated before. They are mass moment of inertia. It's just before we call them IX, IY, IZ, because we do not consider two subscripts for mass moments of inertia. We didn't consider it because we didn't have to. Now, if you want to generalize the inertia property of a three-dimensional object, of course, the subscript doesn't have to be identical. It could be XY, combination of XY, YZ, and ZX. So these three, in general, by definition, we call them mass moment of inertia, and these three, we call them mass products of inertia. So basically, these two are different. So let's start with the one that we know, mass moment of inertia. And to calculate mass moment of inertia, as you know, I equals to R squared dm, integrated over the entire volume, right? That's by definition. Now to do this, of course, you want to know what is the volume. You have to find out what's the total volume. And so here, what's total volume? I'm sorry, total mass. Total mass is mass density times volume. So the unit mass equals to mass density times unit volume, like we did before. So here, the problem becomes finding the definition of this volume. Now, because this is a regular shape, so you actually will know how to do the mass, right? So what's the total volume? So in this case, total mass equals to mass density rho times the total volume. And what's the total volume is actually a squared times h divided by 2. Do you agree? Right? This one is super simple. So this we know is 1/2 of a squared times h divided by 2. So this whole thing is the total mass. Of course, multiplied by mass density. So we figure this one out first. Now, next, calculate Ix. Take the first one. To calculate Ix, if you look at the xy axis, of course I rotate this way because y coincides with this one, so you're gonna look from the bottom. And of course, to do this calculation, we need to figure out the relationship between x and y. And this is the volume. Correct? Now you have different ways to do this calculation. Now, what you can do is to take a slice. You can take a slice horizontally or vertically. In this case, it doesn't really matter because it's the same. You have the same dimension on both the x and y axis. So if you take a slice, this is on the y-axis, and make this to be dy. And the center of this dy is going to be at this point. And on the x-axis, this is going to be the variable x. And this unit strip or unit slice will keep changing the value of x. When it's at a, on y-axis is 0. When it's 0, on the x-axis it becomes a. But the center of this unit strip, as we know, is what? Is half of x, correct? It's just half of it because they're at the center. So here is x over 2. However, what is the linear equation of the function? The linear equation of this slope, as you can see that we know that when x is 0, y is a, and x is y, and x is a, y is 4. So that means x plus y equals a. Do you agree? Right? So x plus y equals a. And that means what? That means you already have these two. You can say that x equals to a minus y, or you can say y equals to a minus x. Correct? Right? Okay, and then we can start putting numbers to find out what is Ixx and what is Iy. So let's start with the first one. And now we're going to integrate the whole thing in using this unit volume. So Ixx equals to, remember, mass density, take it out, and integrate dV for the entire volume. And don't forget that within this integral, you also have r squared, right? We had to put in r squared, and r must be the direction perpendicular to x. So in this case, you can use y squared with dm. Remember, this must be perpendicular to x. So here, rho times y squared and this. So what is dV here? If you use this, look at this. What's the volume of this unit strip? The unit strip is dy times x. and times the height. And the height is constant h. So can I say that dv is nothing but just x times h times dy, right? So that's x times h times dy. Now, don't confuse x with h. H is a constant, x is a variable. Now you just plug this thing into this dv right here. Of course, since we have decided to use dy, you may want to replace x with what?